Give me one pasta. Now that I've got my pasta in there, I guess all I gotta do is turn it on. Ah! That didn't take as long as I thought it would.
Ma'am, you are under arrest for violating the laws of thermal energy.
Thermal energy? What's thermal energy?
Ignorance of the law is not an excuse.
A bandana? Where are you taking me?
Thermal Energy HQ. You need to be re-educated.
Where am I? What are you guys doing to me? What is the point of this?
Thermal Education 101. Here at Thermal Education 101, we have a few objectives that all clients must learn. Now, can you explain how energy is transferred during warming and cooling at the microscopic level?
I have no idea what you just said.
Oh, well, what about naming and describing the energy transfer mechanism involved in the process?
What are you talking about?
Explain how a thermometer measures the temperature of an object.
I have no idea.
Oh, you. Describe how the Celsius temperature scale was established.
How am I supposed to know
Okay,
these things?
You're kind of starting to get my nerves. Describe how two objects reach thermal equilibrium macroscopically and microscopically, please.
Magically. How else?
Use a temperature time graph to identify when thermal equilibrium is achieved.
I have no idea!
State the physical meaning of heat capacity.
What?
Describe the relationship between mass, temperature change, and thermal energy.
Oh my god!
Use this relationship to predict amount of energy transfer or a change in temperature for specific situations.
I'm gonna cry, man!
Here at Thermal Education 101, we have a few punishments for ignorant fools such as yourself.
Not that! No! Freeze! Wait, who are you?
That does not matter. All that matters is I will teach you how to answer the objectives.
How?
Just watch the video.
The faster moving particles in the warmer object collide with the slower moving particles in the cooler object, thus transferring their kinetic energy to the cooler particles. This causes the temperature to equalize over time. This process is known as diffusion and is completely random. See? We're moving at the same speed now. A thermometer works through thermal expansion. A substance is put into a glass vial. This substance then thermally expands accordingly due to the temperature of the environment. Anders Celsius developed his temperature scale by using a mercury thermometer and the boiling point and the freezing point of water. Here, Mr. Celsius marked it as 0 degrees. Here, Mr. Celsius marked it as 100 degrees. The two objects, one hotter and one colder, are in contact with each other. Their temperatures will equalize over time. As you can see now, the two objects have reached thermal equilibrium. My ex-Siamese twins' yellow apples represent the faster moving particles of a hot object, whereas my own green apples represent the slower moving particles of a cold object. Through random collisions, the temperature of the two objects reaches thermal equilibrium, and the net energy transfer is 0. Here is a temperature versus time graph that shows a case of thermal equilibrium. As you can see here, the lines meet, signifying that the net energy flow is equal to 0.
The specific heat capacity of an object is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius.
But comrade, how is specific heat capacity useful? Well, you see there is an equation where you use specific heat capacity times the mass of an object times the change in temperature in the object equals the change in thermal energy. This problem is very useful in many questions in life.
But I have a question. If I have a 200 gram steel pot that's heating 100 grams of water, And they both begin and end at 20 and 100 degrees. What's the amount of ETH going into both?
Okay, so for this problem, you gotta use the equation specific heat capacity times mass times the change in temperature equals the change in thermal energy. So let's look at the 100 grams of water first. So the change in thermal energy for this is equal to 4.184 joules over grams times degrees Celsius times 100 grams and the change in temperature, which is 80 degrees Celsius. Now these units all cancel out, only leaving the joules. So basically, you got 4.184 joules times 100 times 80, and that's equal to 33,472 joules. Now on to the 200 gram iron pan. So the change in thermal energy is equal to 0.45 joules over grams times degrees Celsius, the specific heat capacity. And then you multiply that by the mass, 200 grams, and you multiply that by the change in temperature, which is 80 degrees Celsius. And once again, the units cancel out, leaving you with 0.45 joules times 200 times 80 equals the change in thermal energy, and that gives you 7,200 joules.
Why did they require different amounts of thermal energy?
Alright, so look at this. This is the specific heat capacity for water. Now look at this. It's the specific heat capacity for iron. Alright, so you look at this. This is, say, about 9 times lower than this. Now, that means that it absorbs 9 times less energy for the same amount of temperature change. You know what I'm explaining? So, that means that water absorbs so much more energy, and that's why, despite the fact that they have the same change in temperature, they have such a different change in thermal energy.
Thanks for the jacket, guys. But why is it so hot in here? Can you help me? Sure I can. Your black jacket has a very low albedo, meaning that it does not reflect light. That means that the energy from the light is absorbed into your jacket and it changes into thermal energy, radiating as heat and making you feel hotter.
Thanks, Mr. Disappearing Hobo Man.
I'm a proud graduate of Thermal Education 101.